morning or good afternoon, depending on where you are in the world. Thanks for joining. My name is John Tinsley. I'm the CEO and co-founder of Iconic Translation Machines, and I'm happy again to deliver this webinar. I'm coming to you from Dublin, Ireland. It's the hottest day of the year in Dublin. I'm in my home office, but I cannot open any of the windows because there's construction going on outside and it's very noisy. So I'm quite warm. But anyway, for those of you who joined us last week, welcome back. Thanks for attending again. For those of you who missed last week and are here for the first time today, you're very welcome. And for those of you who joined last week but are not here today, obviously you're not here, but we know who you are. So this is the second in a three-part webinar series entitled Neural Machine Translation, the Past, the Present, and the Future. Last week, we took a look at the history of Neural MT from its relatively recent inception up to the present day. And in today's webinar, the present, we're going to focus on the current state of the art in Neural MT, what the open challenges are, and where researchers and developers have been focusing their time, effort, and resources over the past year or so. If you weren't here for last week's webinar, don't worry. Hopefully today's content should be should work relatively well on its own. And before we start, again, a little bit of housekeeping. As with last week, the whole webinar is going to be short and sharp, no more than 30 minutes. There's a little bit more content this week, so I'll probably speak for 20-25 minutes. So there might not be a lot of time for Q&A at the end, but we'll see how we go. If there are questions, I'll do my best in the time that we have. Otherwise, I'll follow up afterwards. So pop your questions in the chat box at any point when you have them. And like I said before, we'll be making the webinars available to you online and then publicly once the series is over. So as a brief recap of where we concluded last week, I mentioned that while Neural MT is now clearly the state of the art, our work is far from done. There are a lot of open research questions and practical challenges to be addressed that ought to keep us busy for some time yet. These are broadly summarized here on the sole of David Brent's shoe, as you can see. They range from issues to do with terminology, domain adaptation, language modeling, and more. So as a company, Iconic, working with emerging technology like Neural MT, it's really important that we keep our eye on the balls as things evolve. If we pick a particular implementation of Neural MT and rest on our laurels, we can quickly fall behind. So internally, when Neural MT came on the scene, we needed to find a way with which we could continue to work on production deployments and client needs while also staying up to speed with latest developments in the field. That started as a reading group between our scientific teams and ultimately manifested itself in our Neural MT Weekly blog, which I referred to before. So what happens internally actually is that each week we pick a paper on a particular topic of interest and we look at it through the prism of its overall value, but also its readiness in terms of practical deployment, i.e., can this improve upon what we currently have, and can it improve upon it today? Can it do it quickly? So we started this blog in July 2018. The first issue was called Scaling Neural MT, which focused, as the name suggests, on decreasing the amount of time it takes to train engines, which at the outset was quite some time despite the massive computing power behind it. And so the intro to this post went, let me read this off. Training a Neural MT engine is a time-consuming task. It typically takes a number of days or even weeks when running on powerful GPUs. Reducing this time is a priority for any Neural MT developer. And in this post, we explore recent work by Ott et al., whereby without compromising on translation quality, they speed up the training time by 5 times on a single machine and by 38 times using 16 such machines. That was a good improvement and very topical at the time. At the other end of the spectrum, 22 months later, in May 2020, our most recent issue, number 83, was called Selective Attention for Context-Aware Neural Machine Translation. And this topic relates to the idea of using more than just single sentence context when translating any given segment of text. And you'll hear a bit more about that particular topic next week when we take a look forward. But the point I'm trying to make here is that taken as a whole, our Neural MT blog provides quite an accurate snapshot as to which topics researchers and developers have been focusing their efforts on. So what we did for the purposes of this webinar is collect all of the blog posts we published, excluding a few special editions on use cases, categorize them by topic, and look at the distribution of topics across the whole blog series. The findings which you see on the screen here now give you that kind of picture of the R&D landscape within the Neural MT field. So looking at the most prevalent topic in blue, we call model improvement. This is a bit of a catch-all category for posts and papers which looked at more fundamental general improvements to the underlying neural MT algorithms. And this accounted for almost 20% of all of the posts on the blog. This is actually a more recent development as well. So around half of those posts actually came in the last 6 months or so. Probably the most preeminent of these works was issue 32, entitled The Transformer Model, State of the Art Neural MT, which took a look at Google's paper that didn't use one of the traditional approaches using recurrent or convolutional neural networks. Rather, it introduced the concept of the attention mechanism and feed forward layers at various levels of the network to train the whole end-to-end pipeline. Other model improvement posts looked at other types of self-attention models, transfer learning, noisy channel modeling, etc. So aside from model improvement, the remainder of the posts looked at more specific topics. So there were 14 of them dealing with terminology, 11% dealing with multilingual MT, just under 10% on data creation and low resource languages, as well as another 10% on domain adaptation. So if we take a look at this data from another angle, we can actually see how many articles this corresponds to. As for those ones above 10% that I've mentioned already, I'm going to go into them in a little bit more detail shortly. But aside from those, other recurring topics in the series have included 5 posts on language models and robustness, 4 posts on speed and scaling of neural MT, and others on evaluating MT, incorporating contextual information, data cleaning, data preparation, speech translations, and more. So of those ones on the long tail that you see there, I'm going to summarize each one of them briefly to give you a bit more background on them. So firstly, language modeling. And this is the idea of using monolingual target side information in order to inform the translation process. For example, if we're translating from French into English, we might have a massive model representing the English language, which is in some way used by the translation algorithm to help it decide what the best translation is. At the beginning, these weren't widely considered for supervised neural MT, but then came the idea of what is known as BERT, or bidirectional encoder representations from transformers. It's a bit of a mouthful. And these are language models that look at both left to right and right to left contexts of the language, hence the bidirectional aspect. And these models, especially when pre-trained and have broad coverage, are really popular and have shown quite impressive results across a variety of different NLP tasks. But researchers are still continuing to kind of explore how these can be effectively incorporated into neural MT models. So I'd encourage you to take a look at issues 68 and 70 of the blog for a little bit more detail on language modeling for neural MT. Secondly, number 2, robustness. So broadly speaking, the idea here is to reduce certain types of errors that seem to be specific to neural MT. So for example, we have undergeneration, which is basically missing chunks of translation in the output, which is not very reassuring. You may also have seen examples of overgeneration, which is essentially where the engine gets stuck in a loop and repeats the same word or phrase many times over in the output. So the first step in resolving these types of issues is to understand exactly why they're happening. And in many cases, the answer is noisy training data. So making sure that the data is as clean as possible is crucial. And other lines of research have included so-called copying, or identifying certain entities in the source that, rather than going through the translation model itself, should just effectively be copy and pasted into the translation output. And lastly, it was identified that a number of issues were systematic in nature, which is always a good type of issue to have, though not necessarily easy to detect, and thus would be good candidates to be fixed automatically as a post process. This is so-called neural automated post editing. And again, I'd encourage you to check out issues 10 and 35 of the blog post specifically for more details on robustness. Thirdly, speed and scaling. It's relatively self-explanatory. We want both the training to be faster and the translation to be faster. So how is this achieved exactly? So going back to that very first post I referred to earlier, one approach is just to make better use of the hardware at our disposal. And effectively what's happening with neural MT is we're repurposing hardware that's been optimized for one task. So this is GPUs, which have been developed for graphics processing, and we're trying to adapt it for another task. Thus, we're still really exploring the best ways in which to do this. So if you go back and check out issue 1, you'll see a lot more information on things like half precision floating points, which will kind of explain that in a little bit more technical detail. The other point is related to improving the efficiency of the algorithms themselves, such as optimizing the beam search or pruning the search space, both of which were topics that were relevant in statistical MT. Additionally, there's been work on the idea of so-called control networks, which try to more efficiently use large models without sacrificing translation quality, let's say, as opposed to using smaller, faster models, which might not be as good at translating. So again, you can find a little bit more information on these particular issues in issues 17 and 72 of the blog series. Lastly, the hot topic of evaluation. Are existing automatic metrics such as BLUE, Meteor, and TER still effective for neural MT? So you might be looking at me now thinking, were they ever effective? So the question here might be actually, are they even less effective now than they were before? And the theory might be yes, because we're getting different types of output, and these metrics were not developed for like the more fluent style of translation that we get with neural MT. So there has been some work on different types of metrics that maybe are more suitable for neural MT, such as character-based assessments. But for now, the old favorites are still very much in circulation, and it doesn't look like they're going to go away anytime soon. More to the point, now that we undoubtedly have better MT quality, the question of how do we run better human evaluations to perhaps avoid exaggerated claims. So as I mentioned last week, the topic of human parity for machine translation caused a lot of waves, and there has been extensive work recently on how to design and implement rigorous evaluation setups. So a recent paper that I alluded to last week by a number of leading researchers on the topic set out 5 broad recommendations in this regard, ranging from the assessors themselves to the test sets being used and the methodology for actually coming up with scores. So the recent issues 81 and 82 of the blog covered this particular paper in a 2-part post from our own team summarizing the work, and then a second post from one of the authors themselves. So I definitely encourage you to check that out. And I actually think there might be another webinar hosted by Taus later on today with actually some of the same people covering that topic. So there's a shout out to those guys. Okay, let's now go back and take a closer look at some of the more frequently recurring topics on specific issues that I mentioned already, namely terminology, multilingual MT, data creation, and domain adaptation. So let's start with everybody's favorite, terminology. I'm actually really conflating 2 topics here, as the title suggests. One deals with the translation of unknown words or out of vocabulary terminology, while the other deals with the translation of words in specific ways, so kind of more like glossaries. So let's look at unknown words first. So the first issue that arose with neural MT was how it handled words it hadn't seen before. With statistical MT, the source word was simply copied into the target if we didn't know it. So if we're going from Russian into English and we didn't know how to translate a particular Russian word, that Russian word just appeared in the output. Thus, we could identify these and perhaps treat them as a post-process backing off to a dictionary or something like that. But with neural MT, there was no such explicit link or alignment between the source and the translation. This is lost somewhere between the encoder and the decoder layers. Thus, unknown source words were simply omitted from the target or replaced with an unknown token like you see in the example there. So the Russian to English translation was method and apparatus for unknown in container unknown. It didn't know how to translate those words. And obviously this is not desirable, particularly if it was going to be in any way frequent. So the proposed solution was to split words into subwords down to even the character level using an approach called byte pair encoding, or BPE. This is based on the intuition that various classes of words, such as in heavily inflected languages like Russian, or compound languages like German, or character-based languages like Chinese, that these classes of words are translatable actually in smaller units than just the word. And this actually worked really well to the point that it's pretty much a staple in today's neural MT engines. So you can see the example on the slide there of how this subword translation process works for this long German compound word that you see in the reference, where basically we didn't have that word in our vocabulary, so we started to break it down into various subwords and try to translate them to see if we could get a reasonable translation. And like I said, this has worked very well. Clearly, it's going to be more effective for some languages than others, but ultimately, it does remove the issue of untranslated words in NeuralMT completely, which is the outcome that we wanted. As for terminology itself and specifying how certain words are translated, this is a much bigger fish to fry. So mainly, it's one of the key issues that held up NeuralMT from being production ready out of the blocks. Partly because this was an issue that was solved for statistical MT. Like you see in the example, I went for a drive to check if my eyesight was okay. With statistical MT, we could put tags around certain words to tell the decoder to translate them in this way. So in this way, we put tags around my eyesight and tell it, translate this as la vista, and translate the rest of it however you want to. And we were absolutely sure that my eyesight will be translated in that way. This was in essence a guarantee that is no longer there with NeuralMT, due in part to the fact that NeuralMT is an end-to-end process rather than a sequence of steps whereby we have a chance to inject these terms. The fact that this is still an ongoing challenge for NeuralMT is evidenced by the fact that our first post on this topic in the blog was number 7 in August 2018, and our most recent posts, 76 and 77 from April of this year, also dealt with the topic. So early approaches to terminology solutions in NeuralMT were quite simple. They involved replacing a term with a variable in the source that would stay untranslated and then putting back the correct translation as a post process. And this was effective to a point, but could cause issues due to unexpected input and also required external alignment information to know where to actually correctly place the information in the target. A more elegant approach is known as constrained decoding, which essentially restricts the model from choosing certain translations that don't contain specific terms. And actually, the author of this particular approach worked at Iconic for 6 months as an intern to help us implement this in our very first NeuralMT systems that we deployed. But while this approach works well on a high level, it is computationally quite expensive. So the complexity is linear in the number of terms that you want to use. I.e., the bigger your terminology list, the slower the translation will be. So it's always a question of trade-offs. Other approaches include a variety of methods by which models are trained to use certain terms to allow for terms to be injected at runtime with markup, similar to Moses. All of these approaches, like I said, have respective pros and cons, but none of them are as simple and as lightweight as what we had with SMT. So what we found at Iconic is really there is no silver bullet yet here. There's no single ideal way in which to apply terminology. Some approaches are more effective than others, but perhaps they're more cumbersome, i.e. they require us having to retrain the model, which takes time. So ultimately what we do is we look at it on a case-by-case basis, and the approach we go with depends on the engine that we're building and the needs of that specific client in terms of speed, in terms of accuracy, etc. So next up, we are going to look at what is broadly known as multilingual machine translation. This is the idea that we can have a single neural MT model that actually has the capability to translate between multiple languages. So the concept is similar to that of a pivot language, except it's actually inherent to the model rather than being distinct steps. So instead of going, instead of going from English to Russian, then Russian to Korean, we have a single model and do it in a single pass. So this is kind of related to the topic of low resource languages insofar as the broad approach can allow us to translate between languages where we don't have a lot of direct training data. So if we consider the 3 languages on the screen here, English, Russian, and Korean, in practice, we can probably get our hands on a lot of English-Russian data and a lot of English-Korean parallel data, but it's unlikely there's a lot of Russian to Korean parallel data kicking around. So the idea here is that by training a model jointly on English-Russian and English-Korean, that we can indirectly learn then how to translate between Russian and Korean. This is known as zero-shot dual learning, and the implementation here has been referred to as zero-shot machine translation. So in very simplistic terms, the way it works is as follows. As per the example that you see on the slide, we have a Russian to English corpus, and we have an English to Korean corpus. So let's say that the English sentence E1 in the Russian corpus is actually the same sentence as the sentence E7 in the English-Korean corpus. We can therefore infer that the Russian sentence R1 and the Korean sentence K2 are translations of each other. And the same applies for R4 and K1 with the other red line that you see there. And that's more or less it. That's the concept, and it works. It sounds simple, but obviously it's quite complex under the hood, and it's very computationally expensive as well, because obviously we're not just training one model here, we're training kind of lots of one giant model that covers all of these eventualities. So again, this is not a silver bullet. Research to date shows that in this scenario that I just described, we'll actually still get a better Russian to English translation if we just train a Russian to English system on its own, rather than having Russian to English be part of the multilingual scenario. Similarly, in some cases, actually classical pivot approach, like translating from Russian to English first and then from English to Korean, will still come out on top. But this is a massively interesting space and has particularly important implications for low resource languages too. So speaking of which, don't get too worried about the graph on the slide. We'll take a look at the topic of low resource languages, which also accounted for around 10% of all the blog posts. As you probably know, a low resource language can be broadly defined as languages where we don't have a lot of, if any, parallel training data, which to build an MT engine. So the question is, what can we do in this scenario? Obviously, one approach is multilingual MT or pivoting, which I just described. But aside from that, there are two other approaches loosely related to each other that have got the attention of researchers over the last couple of years, namely synthetic training data and unsupervised training. So with synthetic training data is basically the idea of using an MT engine to translate content and create more parallel data, which we use for training. So for example, if we have a small English to Russian MT engine and we have a lot of English monolingual data, we use that MT engine to translate the monolingual data into Russian, leaving us with a large amount of parallel data, which was to train a larger and in theory better MT engine. So this concept is known as back translation. And I can imagine probably what you're thinking now, the output is going to be MT output. It's going to be noisy and low quality, and thus the resulting MT engine that we train on this data will be poor as well. And that's a very sound intuition. That was the intuition of most researchers too, until it was tested empirically, and in practice it has actually worked quite well. So much so that it triggered researchers to begin digging deeper and understanding better things such as, okay, if this actually works, what is the optimal proportion of real versus synthetic data that we should use? What type of monolingual data is best? How good the base MT engine needs to be at a minimum. So it's actually opened up a lot of different channels for people to explore. And in the graph that you see there was some research that was showing, okay, if we keep adding more and more synthetic data, at what point does the quality trail off depending on the approach to neural MT that we're using. So as you can see, it opened a bit of a can of worms. And we too at Iconic, we were quite skeptical about this approach at the outset, but we had a client need for a Turkish to English legal MT engine that we didn't have a lot of data for. So we tried out this approach. It worked really well. And I would say it's now, it's very much a weapon in our arsenal when we're looking at building MT engines for clients. As for unsupervised training, there's the shrugging emoji there because there's not really a good graphical representation of this. It's a pretty technical topic. But essentially, it's the idea of training an engine without any parallel data to begin with, as opposed to supervised learning, which is the standard approach where we have training data. So in theory, we have no bilingual data at the outset, but in practice, there's often some seed data, like a bilingual dictionary or word embeddings. And then after that, we have approaches such as cross-lingual word embeddings and adversarial training. And these are used to initialize an MT engine. And then training cycles iterate to optimize the performance against some objective function, such as a language model score. And basically, we keep iterating the training until we're happy with the performance, generally speaking. So there's been a lot of research on this particular topic. So if you're interested in reading more, I'd encourage you to check out particularly issue 28 of the blog, which subsequently links to a lot of different pieces of research on different approaches to this particular topic. Last but not least, domain adaptation. So again, the concept here is that rather than having separate engines for different domains or different content types, is that we can train on all of the data that we have across multiple domains and then somehow adapt the system on the fly to a particular input. Does this work? The short answer is yes, it does. And this is particularly important because, as we mentioned, neural MT engines are not great at generalizing with things they haven't seen before. So if we have a legal MT engine, it's really not going to do well if we try to translate clinical trial content or pharmaceutical content with it. And domain adaptation is another topic that has run the full gamut of the blog, starting from issue 9 and continuing to issue 71. So the basic standard approach for domain adaptation is basically we train a large model partially on generic data to a certain point, and then we finish off the training with in-domain data, essentially tuning the parameters towards the in-domain data at the end. So if neural MT works in training stages or epochs, so we stop at a certain point and then add in the new data to top it up more towards that data. And one particular approach that has worked really well based on this idea is what is known as on-the-fly adaptation, whereby the hyperparameter settings in a neural MT model are dynamically adapted on the fly. So essentially, our MT model is trained on data from multiple domains, like is illustrated on the slide there. And then for each input segment that we want to translate, similar sentences are identified in the neural model using information retrieval techniques. And then the model parameters are essentially temporarily retuned and updated to suit that input, carry out the translation, and then reset for the next input. So it allows us to kind of, like I said, adapt on the fly to whatever we're trying to handle. So there are, of course, as a caveat with everything, there are overheads with this approach in terms of the computation. This is slower than just a standard non-adaptive MT engine. But what we found in practice is it works really, really, really well, particularly when the multiple domains have some similarity, perhaps on a lexical level, but are ultimately distinct enough. So the example illustrated there might not work because our pharma is quite different from our, from our Europarl or from other data. But if we're just looking at, let's say, the life sciences, maybe we could have pharma, clinical, regulatory in one engine, which have a bit of overlap but are distinct enough to allow this domain adaptation to work pretty well. So conscious of the time and conscious of the fact that I've covered a lot of ground here, I'm going to wrap up at this point. I mean, I would say there is quite a bit of homework to go away with. I've referred to a lot of posts which will make for some good follow-up in terms of the topics I've covered. So you'll probably find many of your answers there. The time is a little bit short here. I'll have a look and see if there are any good questions that we could cover really quickly. But one thing I would point out is that what we're going to cover in next week's blog is how this particular graphic is going to evolve over time. So these are the proportions of particular topics. Are these topics going to grow over time, or are there going to be new topics? So again, that's one of those ones where I'm going to tell you to stay tuned. But if there are any short questions now that I can address in a minute or two, I'm happy to take them. Otherwise, we can wrap up. And obviously, we'll follow up with you if you have more concrete questions afterwards. Okay. So I'll give you a minute or two to pop some questions in there. Okay, so first two questions that have come in are essentially on topics that I'm going to cover next week around contextual level, more like document level context, and that more domain adaptation and things like that. So I guess I'll draw a line under it here and say we'll cover them in next week's webinar. So hopefully I'll see you all again there. And if there are any questions, feel free to follow up directly with us afterwards, and we'll be happy to do our best to address them. Thanks very much. Have a nice weekend, and we'll see you next week.